Okay, so we are going to look at the phase transitions, and these are the conditions for the equilibrium during the phase transition. Uh, we have this chemical equilibrium, and then we have the mechanical equilibrium, and also we have thermal equilibrium. So we have to deal with these three equilibrium conditions in order to attain the uh, complete equilibrium during the phase transition. Now we are going to look at the classification of. We're going to look at the classification of phase transitions. So, as we know, the Gibbs free energy we use a symbol of G is equal to mu I and I. What does that mean is the mu I is the chemical potential for if you have multiple phases existing in your system, then the mu is the chemical potential of that phase. Let's say there are two phases, so there will be mu one and mu two. So mu one will be the chemical potential for the for phase one, and mu two will be chemical potential for phase two. And N1 and N2 will be the number of particles in phase one and phase two. So, so if we differentiate the G, the the Gibbs free energy with respect to number of particles in the phase 1 or phase 2, we're going to get mu I. Okay, we're going to get mu I. So if you say that in chemical equilibrium, or in general in equilibrium, simply saying in equilibrium, we know that mu1 is equal to mu2. That means delta G by delta N1 should be equal to delta G by delta. So this is from your condition of chemical equilibrium. However, uh, so we are having one restriction on G about its derivative with respect to N. So can we also have restrictions on the derivatives of G with respect to other two variables, that is pressure and temperature? So there is no restriction as such. So delta G by delta P at constant temperature and number of particles, and delta G by delta T at constant pressure and the number of particles. So there is no restriction on these derivatives. So what does that mean is they can have different values. Okay? They need not to be same. They need not to be same like this. So they can be discontinuous. At the transition point. because we just have restriction on mu to be equal to mu 2. We have t1 equal to t2, but not the derivative of g with respect to t and the derivative of g with respect to p. So you can learn from this that actually what these derivative uh, have a meaning, or what this derivative indicate their significance. So for that we have to go slightly backwards for our like first law of thermodynamics. So we can do this by using the first law of thermodynamics. Let me use the different color for that. Okay. So in our first law of thermodynamics, the amount of heat added to the system can be used to increase its internal energy and to do the sorry, it should be delta W to do the work. So this means that D is equal to delta Q minus delta W. Now the delta Q is nothing but T times ds, and the delta W at constant pressure is P times. We're going to use a simple trick here. We're going to add and subtract. Do that first. So let's say we have the derivative of t and s, product of t and s. So that means if we can write this in terms of derivative of t and s, it will be t ds minus uh, s times dt. So, but we already have t ds, so that minus will go on. It will not be there, it will be cancelled. So we will have only s dt. Okay. Similarly, we will do for the derivative of the product of pressure and volume, and here the pdv will be cancelled and we will have vd. All right, now uh, we're going to take this complete like this term and this term on the other side, so that we can write it like this: e minus ds plus pv, which is equal to just this term and this term. So v dp minus s. And if you look at this term on the left hand side of the last equation, this is nothing but G, the Gibbs free energy. So dg is equal to v dp minus s. So what this means is that if you differentiate, take the derivative of g with respect to t at constant pressure means this term will be 0, and it is going to give you simply S. And same thing, you do it with P at constant temperature, you're going to get V. Now what that means is that these derivatives are nothing but the volume and the entropy of the system. Now if you find that S1, that is double G 1 upon double T constant pressure, and S2, that is double G2 by double T, and if S1 is not equal to S2, same thing with V1 equal to double G by double G1 by double P constant temperature, and V2 equal to double G2 by double P constant temperature again. So if V1 is not equal to V2, these two should be at the phase transition point. If these conditions are satisfied, that means S1 is not equal to S2 and V1 is not equal to V2. We call this as first order phase transition. Why first order? Because these S and V are nothing but the first derivative of G with respect to T and P respectively. Therefore, they are called first order phase transitions. So if so, remember that we have for first order phase transition, for first order phase transition, double G by double N1 should be equal to double G by double N2. That means that means mu1 is equal to mu2. Here I should have said not G1 and G2 instead of T1 and okay. No, actually that was correct. The previous one should have G1 and G2 only. And what are the other conditions? That S1 should not be equal to S2 and V1 should not be equal to V2. You can always convert this V in the form of P as well. If S1 is equal to S2 and V1 is equal to V2 along with mu1 is equal to mu2. What does that mean is that S1 is equal to S2 and V1 is equal to V2 means these derivatives are having same values, that means they are continuous. G is continuous with respect to T and G is continuous with respect to P. So that means G is continuous for the first order derivative. First order derivative of G is continuous. So then such transitions are called continuous phase transitions uh, or higher order phase transitions, like second order, third order. So this is how we classify based on the continuity of the derivatives of the Gibbs free energy. So if you want to do this graphically, so let's say we want to plot, so if you want to plot G versus T, and if this is the transition temperature, the transition temperature, then so delta G by delta T gives you S. Okay, and so let me show it slightly. So this is what will be. This is the first phase, and this is the second phase. So if you look at the slope here, delta G by delta T will give you the entropy for the first phase, and same thing here, the slope will give you S2. And you can see at this point, S1 is not equal to S2 at the phase transition. That means the G is not continuous. In other words, if you plot the derivative, that means the slope from this curve, so S delta G by delta T as a function of temperature, and this is your TC, then you will see that something like this. So this is the below Tc variation of entropy as a function of temperature, and above Tc variation of entropy with respect to temperature. And this is the transition point where S1 is not equal to S2. So that's the typical first order phase transition. What will happen in higher order phase transition is that this will be continuous. Okay? There will be no discontinuity. That means S1 will be equal to S2 at the transition point. So now let us look at the phase diagram. Okay? So what do you mean by phase diagram? So as we know, the Gibbs free energy G is a function of temperature, pressure, and the number of particles. And what kind of phases we can realize in the nature, that is, what kind of phases can exist, will depend on the phases having the lowest free energy. Okay. The phase exists with lowest free energy. The phases which will have lowest free energy will be exist and will be stable. Depending on whether it is constant temperature or pressure, then it will be Gibbs free energy. If it is constant temperature and volume, it will be Helmholtz free energy. So what is the Gibbs free energy? We can simply write it as the number of particles in the in the system, if we have only one component system here, and the individual free energy. What that means is G is the free energy per particle. that is total free energy is G divided by N, you will get small g. And of course, it will only depend on T and P. So, as we also have in previous expression we looked at, that it is G is also can be written as mu times N. And if you compare these two equations, okay, you will see that mu is equal to G of T. So you can say that the chemical potential is nothing but the free energy per particle. Okay. Now, at the phase transition, mu1 is equal to mu2. That means G1 of T comma P and G2 of T comma P should be equal. Hence, for equilibrium, the Gibbs free energy per particle, that is G1 and G2, in the two phases must be the same. Right? So acceptable. Therefore, if so, what we have, if G1 and G2 are same, then what we have is only T and P. So if you have a function like this, that the function's values are same for the multiple values of pair of temperatures and volumes, so temperatures and pressures. So that also means that the pressure can be written as function of temperature. What this means is, if the temperature varied, pressure should vary. Okay? So if you want to uh, draw this, show it on a graph. So if you have this curve indicating the uh, phase transition, then on this curve G1 should be equal to G2, and below this G1 is greater than G2, and above this G1 is less than G2. So this is wherever you have this G1 is equal to G2, you can say that the two phases can coexist along this curve of pressure being function of temperature. If the phases are like, let's say, if we are dealing with the phases of liquid and vapor, the curve is called as vapor pressure. For liquid and vapor, if the phases involved are liquid and vapor. If you have solid and liquid, then this will be also called as fusion curve. Okay. And you can also have solid to vapor. In that case, it will be called as sublimation. Depending on which are the two phases, you can call this curve as a vapor pressure curve or fusion curve or sublimation curve. So this the diagram of this pressure versus temperature. We can say that this is what we have the phase diagram. Now, if you have a single component, we are going to deal with a single component most often in this course system with two phases. So phase 1 and phase 2. So the Gibbs free energy can also be written, as we have seen in the previous one, that it is summation of mu times n, and we know that mu is nothing but a single particle free energy. So G1 times N1 plus G2 times N2. where N1 and N2 are nothing but your number of particles in the first and second phase respectively. Now, what we got is that G1 should be equal to G2. What this means is that the free energy per particle between two phases are same. That means even if a particle from out of N1 goes to N2, G does not change because G1 is same as G2. That means even if this term becomes smaller, this term becomes large. If let's say some particles from phase 1 are gone to phase 2, that means N1 will be reduced and by same amount the N2 will be increased. So if G1 and G2 are same, we are not going to have any change in the total free energy. So if you similarly, if you have three component system, I mean single component, but with three phases. So two phases means you can have solid liquid, liquid or liquid vapor or solid vapor. Now in three phases you can have solid, liquid, vapor all together. So just by looking at this we will have the condition for equilibrium to be G1 of T comma P should be equal to G2 of T comma P and G3 at T, which means that at when this condition is satisfied, the three phases coexist, and the point at which this happens is called as the triple. And we know for water, this is the draw the water phase diagram. So let's say this is where the liquid is, this is where the vapor is, and this is where the solid is. You think of ice, water, and vapor. So here G2 is equal to G3. Here G1 is equal to G2. Here G1 is equal to G3. And at this point, G1 is equal to G2 is equal to G3. And there is another point which is to be discussed here. That is this point where this curve terminates. This is called as the critical point. So beyond critical point, there is no difference between the liquid and vapor. So very often this critical point is utilized in fabrication of the electromechanical devices where you have a suspension and when you have your device in liquid and when you want to take it out, there will be huge pressure of huge force will be acting from the tension of the surface of the liquid, which might not allow you to fabricate the electromechanical micro electromechanical devices which are suspended and they can collapse because of this surface tension. But if you take your system to this pressure and this temperature, beyond this value, then you know that there is no boundary between the vapor phase and the liquid phase, or gaseous phase and the liquid phase. That means there will be no difference in the liquid and vapor beyond this point, and therefore there will be no problem of surface tension beyond this pressure and temperature. So if we look at the triple point for water, so T, let's call it T0 is around 0.0078 degrees Celsius, and P0 is 0.006 atmosphere. And the critical point for water is around 22.12 megapascal and 647.14 Kelvin. This is for water. Remember, the critical point is the point beyond which liquid and vapor or gaseous phase becomes similar. There is no distinction. Whereas for CO2, the the critical pressure is 7.37 megapascal, and the temperature is 31 degrees Celsius. So relatively, this temperature can be easily achieved, and also this pressure is less. So we often use CO2, uh, the critical point of CO2, to remove to during the fabrication of the micro electromechanical devices. Okay. All right, so this is about our phase diagram. Now we're going to look at the Clausius Clapeyron equation. So as we know, at equilibrium during the phase transition, mu1 should be equal to mu2, and if we take the derivative of this total derivative of mu, we should be able to get delta mu1 upon delta t plus delta mu1 upon delta t times delta p times delta t. This should be equal to delta mu2 upon delta t plus delta mu2 upon delta p into delta p by delta t. And we also know that the g is equal to mu times n. Therefore, the same equations we can write as delta mu I upon delta t will be equal to nothing but 1 by n delta g I upon delta p, which is nothing but the entropy which we have shown in the previous section. Same thing, the V1 or Vy will be equal to delta mu I upon delta p, or it can be written as 1 by n delta g I upon delta p. Okay, let us substitute that this is S1, okay, and this is V1. So S1 V1 double P by double T, ascending minus S2 plus V2 double P by double T. So S1 minus S2 minus S1 is equal to V2 minus V1 double P by double T. Or say that double P by double T is equal to delta Q upon V2 minus V1 times T. As you know that delta Q is equal to T ds, or you can say T S2 minus S. So this is what is called as the Clausius Clapeyron equation. And based on this equation, we can discuss the phase transitions also. So if V2, if let's first discuss about the delta Q. If delta Q is greater than 0, that means the change in heat is positive. Uh, that means the transition takes place with the absorption of heat. So this you can say that it is an endothermic transition. Now, if you have V2 greater than V1, so look at the Clausius-Clapeyron equation and see what will happen if V2 is equal to V1. Sorry, V2 is greater than V1. Then that means V2 greater than V1 means this will be a positive quantity. This will be a positive quantity, and delta P by delta T will be positive. That means when pressure increases, the temperature also increases. Okay? Or you can say the temperature increases with pressure. You can think that this is example of this kind of. This is the boiling of water. Okay. If you increase the pressure, the boiling temperature increases. V2 less than V1, that is delta P by delta T is negative, and this is that means the phase 2 is having less volume than the phase 1. So you can think like this is the melting of ice. Okay. Because we know that ice has more volume than the liquid water. So we have to have basically the pressure volume of the pressure temperature relation. Okay, so we should have the pressure in terms of like the temperature. What can be the expression for this? So if we go back to our Clausius Clapeyron equation and use the ideal gas condition. Okay, then what do we have here is delta P by delta T is equal to, so V2 minus V1 can be written as V2 minus V1. So if I want so you can think of dV here, and that will be equal to P by RT. So from here V is equal to RT upon P, and do is V is equal to RT P, and then therefore V2 minus V1 basically say it as dV, and this will be the derivative of V respect to just a minute. Let's express this in terms of ratio. So P is equal to V, and then take the derivative of P with respect to T. So what we get? It is R by V. What we have here is delta Q. So delta Q upon V2 minus V1. So if we would have taken this, so dV over what we are taking the derivative, that is forgot about this. There's a T in the denominator. So let's so delta Q as it is. Now let's think about V2 minus V1 uh, into T. Okay, so V2 minus V1, let's say it's you can think like the liquid to vapor transition. So the V2 is the volume of the vapor, and V1 is the volume of the liquid. So you know that vapor occupies very large volume as compared to the liquid. So you can neglect V1. So you can neglect if V2 is very greater than V1, then you can think only V is there. So if V is there, so now you can substitute for V is equal to RT by P. That means P coming here and RT here, and there is already T here. So that means you have dP by dt equal to P delta Q upon T square. And if we integrate this equation, that means if we do it like this, that P by double P by P being equal to delta Q by R double T by T square, we would get uh, relation. If we integrate this, we get P equal to P0 e to the power minus delta Q upon you see here ln of this will be integration will give you ln of P with limit from P to P0, and then here delta Q by R outside, and double T by double T by T square the derivative that will be equal to if we start with T is equal to 0 and to T, then that will give you upon R upon T 1 by T integration of 1 by T square with respect to dt will give you 1 by T simply with minus sign. And when you take out the ln on both the sides, you will get P is equal to P0 e to the power minus delta Q upon RT. This shows that as the temperature is increased, temperature is in the denominator of the exponent, the vapor pressure increases because there is a minus sign to the exponential. And if delta Q is a latent heat of vaporization, so we can think of that delta Q being a latent heat of a vaporization, which is required to increase the temperature of the system further. Alright, so with this we're going to stop it here. I'm going to give you more videos